Hello and welcome to the recording for Lab 4. Lab 4 was last Friday for Math 1090. As I said in the lab, I will provide a recording for this lab doing the solutions, but this is not guaranteed for future labs. So with last week and in future weeks, we will be having in-person labs. So we'll get going. So the first question is saying, using integration by parts, solve I1 is equal to the integral of e to the minus 2x sine x by 2 dx. Okay, so before we get going on that, I am just going to give a brief reminder of what integration by parts is. So integration by parts when you are trying to solve an integral with two functions contained within it, let's say f at x and g at x, f at x and g prime at x is actually what we're going to have, dx, then the answer to this integral is this, f at x, g at x, minus the integral of f prime at x, g at x. So it's just it's a reverse of which one has a derivative from the start over here. And of course, you could rearrange this and have the integral of f at x, f prime at x, g prime at x, no, sorry, just g at x, dx is equal to f at x, g at x, minus the integral of f at x, g prime at x. So you can rearrange this equation and have the have it flip there. But because you get to decide which function is f and which one is g, it's not really necessary to do that, but you are able to if you want to show that there. So starting with this first question that we have here. So for I1, and this I sub 1. Okay, so first what we will do is we will determine what these, what are our functions going to be for integration by parts. So let's say I'll do that in green for whenever we're doing this. So basically I need to decide which one is going to be f at x and which one is going to be g at x. So I'm going to say f at x is going to equal to e to the minus 2x. So from here, I'm actually going to do it in multiple colors, but I'll try to keep that consistent just for labeling. And then my g prime at x, which somehow the pen size has changed, is going to be sine of x by 2. Okay, and before we can get going on that, it is easier if you just determine what the derivative of f at x is. F prime at x is going to equal to, we know that if we ever have e to the x, its derivative is just the same function, but because there's a function contained within it, we're going to be using chain rule. So it will be minus 2 e to the minus 2x. And then since we already have g prime at x, we need g at x. So g at x is going to equal to, so it's the antiderivative of sine, and the antiderivative of sine is cos. We keep the inside the same, x by 2. But because when we're going back, so we're doing the opposite, so we flip the trigonometric function, keep the inside the same. If we were be going from g to g prime at x, we would be then multiplying by the derivative of the inside. Now we're going to be dividing by the derivative of the inside. So we'd be dividing by half, which is the same thing as multiplying by 2. And then to go from cos to sine, when we're finding the derivative, we have to multiply by negative. So because sine doesn't have a negative, we need a negative here so that it'll cross out when we do that. So we then have all of the information we need to move back to the integral. So we can say I1 is now equal to f at x, so e to the minus 2x, g at x, so that is times minus 2 cos x by 2, minus the integral of f prime at x, so minus 2 e to the minus 2x, and then times g at x, which is minus 2 cos x by 2, and of course at the end there dx. And so that is our integration by parts there. And so what we'll actually do is we'll just do some simplifying to start. So the next line, let's take this -2 and just put it out up front. So minus 2 e to the minus 2x times cos x by 2 minus. So then we have a minus, a -2, and a -2. So there's 3 negatives there. So altogether that will stay negative. And then we'll take these constants out. So that's 4. Then the derivative of, the integral of e to the minus 2x cos x by 2 dx. Okay. And so that is our first application of integration by parts. But we see here, okay, now we have the integral of e to the minus 2x. We have a cos x, so by 2 dx. And okay, sure, that's different than our original integral, but I still don't know how to solve that. So what I'm actually going to have to do is I'm actually going to have to do a second round of integration by parts. And so what I'm going to do is I'm going to call this part of the equation here, I'm going to label that E. And so we're going to do an aside and solving for E. So for E, and I'll do this in red. Well, I'm going to have to do another integration by parts. And so you're like, okay, we just did this. It's probably going to be a similar thing because all that's different between here is sine and cos. But bear with me and I'll explain that at the end. So let's do that second integration by parts. So once again, we say f at x is equal to e to the minus 2x, which would make f prime at x equal to -2 e to the minus 2x. Then we have, and that is from here. And then we have g prime at x is equal to cos of x by 2. And g at x is then going to be 2 sine x by 2. And our negative sign here, our lack of negative sign here is fine, because going from sine to cos, when we're finding the derivative, we don't have to add a negative. So we have that there. And then, oh, that's not what I wanted to do. We'll move on down. Okay, and so now we're solving for E. So then we say E is equal to, so that's right here once again, and I just didn't label this purple there. So E is equal to f at x, so e to the minus 2x, times g at x times 2 sine x by 2 minus the integral of, we have f prime at x, so minus 2 e to the minus 2x, and then g at x, so that is times 2 sine x by 2 dx. And once again, I'll do some simplification. So I have 2 e to the minus 2x times sine x by 2. We have 2 negatives this time, so that becomes positive. And we have 2 2's, so that's 4. And then the integral of e to the minus 2x times sine of x by 2 dx. Okay, I then look at e to the minus 2x sine x by 2, and I'm like, okay, I still don't know how to solve that, so what are we doing? Well, if we look back at the start, we actually find that we found the original integral within e. So we can actually rewrite this as equals 2 e to the minus 2x sine x by 2 plus 4i1. Okay, and if we sub in this e back to our I1 equation up here, then what we actually find is we have an I1 on this side. Let me switch colors. We have an I1 on this side, and we'll have an I1 over here. And so we can rearrange for the put all the I1s together, similar to when we're solving for x, and that's going to get us to our solution. So we'll go ahead and sub that in. So that means I1 is equal to, back to I1. So I1 is equal to minus 2 e to the minus 2x cos x by 2. And then minus 4, and it was e. So e is now everything that's contained here. So minus 4 times 2 to the e minus 2x sine x by 2 plus 4i1. And once again, this is e. Okay. So we're happy with that. And so now what we'll do is we want to rearrange to solve for I1. Okay, so we have I1 is equal to minus 2 e to the minus 2x cos x by 2 minus 8 e to the minus 2x sine x by 2 minus 16i1. Okay, so we have no more integrals in here. Obviously, I1 here is still an integral, but we can put these together. So we have 17i1 is equal to minus 2 e to the minus 2x cos x by 2 minus 8 e to the minus 2x sine x by 2. And we will be at our final step here. Is then all we need to do is divide both sides by 17. So I1 is equal to minus 2 e to the minus 2x cos x by 2 minus 8 e to the minus 2x sine x by 2 over 17. Okay, and so this is actually our final answer, and I am just going to make sure that that's the matches with mine. Minus 2 e to the minus 2x cos x by 2 minus 8 e to the minus 2x sine x by 2 over 17. That is correct. If you wanted, you could factor out the minus 2 e to the minus 2x here, so we will do that. So we have minus 2 e to the minus 2x cos x by 2 plus 4 sine x by 2 all over 17. And there is just one thing I forgot here is once we have this this e here, so we actually want to have our plus c being placed inside each of these. So this would be plus C, plus C, plus C, plus C, plus C. And if we were to have kept that C around when we're doing all the algebra, so when we're dividing by 17 and that sort of stuff, you're like, well, shouldn't it be C over 17? No, because the C just means there is some constant. We don't know what it is. We're able to keep that out of that algebra there. So that's just a rule for the integrals. So yeah, so we have a plus C there, and this is our final answer. I1 is equal to this. So that is our answer for problem 1A. Okay, and all right. Yeah, so this is question 1A. There we go. Okay, and so we will then do the second one here. So let's just get some space. So question 1B. So that is still same question of using integration by parts, but for I2, which is equal to from 0 to pi by 4. So the integral from 0 to pi by 4 of x cos 2x dx. Okay. So first of all, we are going to be doing a definite integral. So the only difference here is if we do so integration by parts with definite integrals is a for the integral from a to b of f at x g prime at x is equal to f at x g at x minus the integral from a to b. I missed one little thing there. This is so f at x g at x from a to b minus the integral from a to b of f prime at x g at x dx. Here you go. And so to do that, we will, so the only difference is we're having to sub in a and b for all of these, for this first part here and for this second integral here. So the definite doesn't change that much. It's pretty much the same process, but the changes is these bounds. Okay. So we will set up our integration by parts. So this is going to be f at x. So f at x is equal to x. F prime at x is equal to 1. And then here, g prime at x is equal to cos of 2x. G at x is equal to sine of 2x. And because we would normally, if we're doing the derivative, we'd multiply by 2, but now we have to divide by 2. So it's sine 2x over 2. And then we are ready to go ahead and start solving. So for I2, we then say, okay, it is f at x, g at x. And so I'm just going to take a drink. So it is f at x and g at x. So we have x sine of 2x over 2 from 0 to pi by 4. Then minus the integral from 0 to pi by 4 of f prime at x. So that's 1 times g at x, which is cos 2x dx. Okay, and this first part here, we're already have everything we need to solve that, but we will hold off. And this second part here, this is just the integral of cos 2x. And so we actually also just did that in our previous example here. So we will go ahead and, oh, I am sorry. Sorry, this is supposed to be g at x, not g prime at x. So this is actually sine of 2x over 2. My bad. So yeah, so this is g at x here. G prime was on the left, it was here. So to do this, then we well, actually, I said we'll wait, but we'll just do this. We'll do operations on both of these terms in each step. So This from pi by 4 to 0 to pi by 4 is going to be square bracket pi by 4 sine of 2 times pi by 4 over 2 minus the 0 version. So 0 times sine of 2 times 0 over 2. So that is the first term here. Minus, move this over a little bit, minus, so the integral of sine 2x over 2, so I can just, what I'm actually do is I'll move this half out, 1 over 2, 0 to pi by 4, and so this is just sine of 2x dx. Okay, and so next line we will evaluate some of this. So this term all goes to 0 because we have a 0 here. And the first term is going to be pi over 8 times sine of 2 times pi by 4 is just pi by 2. Minus 1 over 2. Okay, and then we have the integral of sine 2x. The integral of sine 2x is minus cos 2x over 2. And that's just because that 2, when it comes out, if we were going the opposite direction, so if we're deriving this, then the 2's would cross out, and cos, from cos to sine, we have to add that negative. That's why we add that negative there. And so then this is also from the range 0 to pi by 4. Okay, and sine of pi by 2 is just 1. So this is just pi over 8 minus 1 over 2 times whatever happens in here. And what I actually see is I can actually move that negative out. So what I'm actually going to do is make this plus. So I will take this negative out. Plus cos of 2x. Oh, well, actually, okay, let me do this more clearly. So I will actually just hold off a step to actually start subbing in. But I have a 1 over 2, and then I have a negative 1 over 2 as well. So I can do plus 1 over 4 of cos 2x pi by 4, 0. And actually, this one would have been easier if I would have taken those values out, but not a big deal. So equals pi over 8 plus 1 over 4 times whatever happens in here. So now we're ready to sub that in. So we have cos of 2 pi by 4 minus cos of 2 times 0 equals pi over 8 plus 1 over 4. And so this is cos of pi by 2 minus cos of 0, which is equal to pi over 8 plus 1 over 4. Cos of pi over 2 is 0. Cos of 0 is 1. So this becomes 0 minus 1, which is just negative 1. So this gets a negative brought out here. So this is pi over 8 minus 1 over 4, which we can say that is a perfectly fine final answer. So I2, but we could also say I2 is approximately 0.142699. So that is our solution for question 1, part B. Okay, and so we will continue on. So now we have question 2. Okay, question 2 says evaluate the integral I is equal to the integral of arc cos of x dx. First, we will do an integration by parts. Then we will need to do a substitution. So these are kind of just like hints. So it's saying, just a second. So you could be given this question and just saying, okay, solve it without giving these steps. But these steps are just here. It's like start with integration by parts, then do a substitution. That's how you're going to get to the final answer. So that's why it's giving us both of those there. Okay, so we will start with our integration by parts. So we have f at x is equal to arc cos of x. And the derivative of arc cos of x is equal to -1 over the square root of 1 minus x squared. And that is just a known derivative there. There's nothing that's like, okay, like obvious here that's like, how do you get there? It's just that's one of those rules for arc cos. And then, and I'll label it. So arc cos is here. And then everything is multiplied by 1. So we're going to say our g prime at x is just 1, which makes our g at x equal to x. There. Okay. And so then we go ahead and start subbing in. So I is equal to, we have f at x, g at x. So arc cos of x times x minus the integral of f prime at x, g at x. So we have -1 over the square root of 1 minus x squared times x dx. Excuse me. So this will be x arc cos of x minus the integral of the negatives actually combine together, so positive x over the square root of 1 minus x squared dx. Okay, and so we have done part A is here. And so now we need to start on part B. So that's saying we're going to need to do a substitution. So what I'm going to say is we are going to have to, we're only focused on here for the substitution. And so what I'm going to use as my variables for substitution is I'm going to say u is equal to the square root of 1 minus x squared. And once again, when we're doing substitution, we're trying to look for a function and its derivative, and both of those have to be contained within the integral here. So the derivative of this is going to be the term is going to have an x in it, right? So and that's the key thing that we're looking for here. And so this is a bit of a messier substitution though, so it's not obvious to see it. But if this is my u, then another way to write this is 1 minus x squared to the power of 1 over 2. And so then if I find the derivative du, then what I get is bring the exponent down. So 1 over 2. Keep the inside the same, 1 minus x squared. Reduce the exponent by 1, minus 1 over 2. And dx. And so if I do some simplifying here, then what I end up with is one final thing, sorry. We then also have to, because there's a function contained inside here, we have to multiply by the derivative of the inside. So that would be minus 2x dx. There we go. That looks better. And so these 2's actually cross out. And so what we're end up with is negative x over the square root of 1 minus x squared dx. And we say, hey, look, that's exactly what we need to solve. That's exactly contained here. And so that means when we actually apply the substitution, we will just want to do one final rearrangement before we do. We have minus du is equal to x over the square root of 1 minus x squared dx. And so what that means is that our I becomes x arc cos of x plus the integral of du and negative du actually. And nothing else, because that du contains everything within there. And so we actually get x arc cos of x minus the integral of du, which is just 1, right? 1, sorry. There is a 1 here. So it's like, what is the antiderivative of 1? Well, it's just you add the variable there. So in this case, it's u. So this is x arc cos of x minus u. And because we did the integral here, we then add that c plus c. And then we have to revert to, x. So we get x arc cos of x minus x again was the square root of 1 minus x squared plus c. And that is actually our final answer for question 2. And just checking that with mine. Yes, perfect. Okay. Okay. And so that's question 2, and we'll move on to question 3. Okay. Question 3. Okay, final question is evaluate I is equal to the integral of sine squared x dx. Okay, and we will be using integration by parts. So in this case, though, we only have sine squared, so it's sine times sine. So both of our functions are actually the same here. So f at x is equal to sine x, and f prime at x is equal to cos x. G prime at x is equal to sine of x. G at x is equal to minus cos of x. And that's because there's no negative in the derivative here. And so we do that, we apply integration by parts now. So we get, excuse me, negative sine of x cos of x, and that negative came from here, minus the integral of cos x, so minus cos x dx. And so we have minus sine x cos x plus the integral of cos squared x dx. Okay, and once again, we have something similar to the start where it's like, okay, well, now what do we do? I don't know what to do with that. But we had that in question 1, and in question 1, what we did is we did another application of integration by parts, and we were able to get there. But the question actually gives us a hint. In two parts. So you have first integration by parts. And B, you have trig identity. So we go ahead and use a trig identity. And one of the ones we know is we have that sine squared x plus cos squared x equals 1. And so we can actually rearrange this to get cos squared x is equal to 1 minus sine squared x. And so we will use that. So we have minus sine x cos x plus the integral of 1 minus sine squared x dx. Okay, so we've done this identity, but what was the point? Well, we see that we have a sine squared x here. We have a sine squared x in the original question. And remember from the first problem that we can, as long as we get back to the original on this right-hand side of the integration by parts, then we can combine those i's and solve for I. So we'll do that. So this is minus sine x cos x plus the integral of 1 dx. We're going to separate this minus the integral of sine squared x dx. Okay, and I'll actually replace this with I now. So I have I is equal to minus sine x cos x plus the integral of 1 is just x minus I plus c, because I've computed that integral there. So we're getting close. We combine the i's. So 2i is equal to minus sine x cos x plus c. And then we get I is equal to minus sine x cos x plus x over 2 plus c. And that is our final answer here. And just checking with my sheet. Yes, there we go. So that is the final answer there. And we are happy. So just a reminder, yeah, when you have these integration by parts, if you have something where once you've done it, you get back to the original or it looks similar, that's fine. Doesn't mean you did it wrong. And also at this case, you could have done integration by parts again, and you would have arrived at the same answer. But we just used the trig identity to get to sort of short circuit that operation there. And so then we have I is equal to minus sine x cos x plus x over 2 plus c. And that is our final answer for the third problem. Okay, if there are any questions, you can send me an email, and our next lab will be occurring on next Friday. So that would be the 11th. And I hope you all have a great week.